Welcome to Slumbertainment. Get comfortable, close your eyes, and let yourself relax. Tonight we explore the history of astronomy. Please like and subscribe for more restful content. Now, let's begin. Long before there were cities or written languages, before the first stone was carved or the first wheel turned, human beings looked up at the night sky and wondered. It was a darkness unlike any we know today, unpolluted by electric light, so deep and pure that the stars seemed to press down upon the earth itself. In those ancient times, the sky was not merely something to observe, but something to live beneath, a vast canopy that governed the rhythms of existence. The appearance of certain stars marked when to plant and when to harvest. The phases of the moon told communities when to gather, when to hunt, when to prepare for the changing seasons. The sky was a clock, a calendar, and a map all woven into one. The earliest astronomers were not scientists in the way we understand the term today. They were farmers and priests, navigators and storytellers. Yet their observations were meticulous, their records surprisingly accurate, and their curiosity boundless. In Mesopotamia, between the Tigris and Euphrates rivers, the Babylonians studied the heavens with a devotion that would span thousands of years. They divided the sky into sections, tracking the movements of planets against the fixed backdrop of stars. They noticed that while most celestial objects moved in predictable patterns, 5 wandering stars moved differently, drifting through the constellations in strange loops and reversals. These wanderers, which we now call planets, fascinated the ancient observers. They recorded their positions on clay tablets using cuneiform script, creating some of the oldest astronomical records ever discovered. The Babylonians developed sophisticated mathematical systems to predict celestial events. They could forecast lunar eclipses with remarkable precision, understanding that these dramatic occurrences followed regular cycles. They identified the zodiac, that band of constellations through which the sun, moon and planets appeared to travel. Their observations were not merely academic exercises, but were deeply intertwined with their understanding of the divine and the ordering of their society. The movements of celestial bodies were believed to reflect the will of the gods, and those who could read the heavens held significant power. Across the ancient world, other civilizations were conducting their own observations with equal dedication. In Egypt, the appearance of the star Sirius just before dawn signaled the annual flooding of the Nile, an event so crucial to Egyptian agriculture and survival that the entire calendar was built around it. The Egyptians aligned their greatest monuments with celestial precision. The pyramids of Giza, those enduring testaments to human ambition and engineering, were constructed with sides facing the cardinal directions with an accuracy that still impresses modern surveyors. The shaft within the Great Pyramid pointed towards specific stars that held religious significance, creating a connection between the earthly realm of the pharaohs and the eternal realm of the heavens. In China, court astronomers kept detailed records of celestial phenomena that stretch back thousands of years. These records are so comprehensive and careful that modern astronomers still consult them when studying historical events like supernovae and comets. The Chinese understood that the sky was not static, but subject to sudden changes and appearances. When a new star blazed into existence, or a comet swept across the firmament, these events were recorded, interpreted, and preserved. Chinese astronomers developed complex instruments for measuring the positions of stars and planets, including elaborate armillary spheres that represented the celestial sphere with interlocking rings of bronze. The ancient Greeks transformed astronomy from a purely observational and religious practice into something approaching what we would recognize as science. Greek philosophers asked fundamental questions about the nature of the cosmos itself. Was the Earth flat or spherical? Did it move or remain stationary? What were the stars made of, and how far away might they be? These questions led to debates, theories, and calculations that would influence astronomical thinking for centuries. Aristotle proposed a geocentric model of the universe with Earth at the centre, surrounded by crystalline spheres that carried the moon, sun, planets and stars in perfect circular motions. This model was elegant, philosophically satisfying, and seemingly confirmed by everyday observation. After all, the Earth beneath our feet feels solid and unmoving, while the heavens appear to revolve around us. Yet even in ancient times there were dissenting voices. Aristarchus of Samos proposed a heliocentric model with the Sun at the centre and Earth as merely another planet, an idea so radical and so contrary to common sense that it was largely dismissed, though never entirely forgotten. Perhaps the most remarkable achievement of Greek astronomy was the work of Eratosthenes, who calculated the circumference of Earth with astonishing accuracy using nothing more than observations of shadows at different locations and geometric reasoning. He noticed that at noon on the summer solstice in the city of Sienne, the sun stood directly overhead, casting no shadow down a deep well. Meanwhile, in Alexandria, several hundred miles to the north, the sun cast a measurable shadow at the same moment. By measuring the angle of this shadow and knowing the distance between the two cities, Eratosthenes calculated Earth's circumference to within a few percent of the true value. This achievement demonstrated that careful observation combined with mathematical reasoning could reveal profound truths about the world. The ancient astronomers worked without telescopes, without photography, without any of the sophisticated instruments that would come later. They had only their eyes, their patience, and their minds. Yet they mapped the sky, predicted eclipses, measured the Earth, and began asking the questions that would drive astronomy forward for millennia. They established that the universe operated according to patterns and rules that human intelligence could discern and understand. In their careful watching of the night sky, in their recording of planetary positions and stellar risings, they were doing something remarkable. They were beginning the long human journey of understanding our place in the cosmos. As the Roman Empire declined, and Europe entered what historians once called the Dark Ages, the torch of astronomical knowledge was kept burning in other parts of the world. Islamic scholars, working in great centres of learning from Baghdad to Cordoba, preserved the astronomical works of the Greeks and added their own observations and innovations. They did far more than simply maintain old knowledge. They expanded it, refined it, and transformed it into something richer and more precise. The Islamic Golden Age, spanning roughly from the 8th to the 14th centuries, represented one of the most productive periods in the history of astronomy, a time when observation and mathematics advanced hand in hand. The Islamic astronomers recognized that accurate observation required sophisticated instruments. They constructed elaborate observatories, buildings dedicated specifically to the study of the heavens, equipped with large and precisely crafted tools. These were not merely places to look at the sky, but centres of research where teams of astronomers worked together, pooling their observations and calculations. The observatory at Maraghe in present-day Iran became one of the most advanced scientific institutions of its time, housing a library and instruments of remarkable size and accuracy. Similarly, the observatory at Samarkand, built under the patronage of the astronomer prince Ulugh Beg, contained instruments so large they were partially embedded in the landscape itself. One of the most important instruments developed and refined during this period was the astrolabe. This intricate device, often beautifully decorated with ornate engravings, served multiple purposes. It could determine the position of the sun and stars, calculate the time of day or night, identify the direction of Mecca for prayer, and solve various astronomical and mathematical problems. The astrolabe was both a practical tool and a representation of astronomical knowledge, its rotating plates and inscribed markings encoding the movements of the celestial sphere. Skilled craftsmen created astrolabes of varying sizes, from large observatory instruments to pocket versions that travellers could carry. The device spread throughout the Islamic world and eventually into medieval Europe, where it became an essential tool for astronomers and navigators alike. Islamic astronomers also developed and improved other observational instruments. The quadrant, a quarter-circle device marked with degree measurements, allowed observers to measure the altitude of celestial objects above the horizon with greater precision than ever before. Large mural quadrants, mounted on walls and sometimes reaching several meters in radius, provided even greater accuracy. The armillary sphere, inherited from earlier civilizations but refined and enlarged, consisted of multiple rings representing the celestial equator, the ecliptic, and other important circles of the celestial sphere. By observing stars and planets through the rings of an armillary sphere, astronomers could determine their precise positions in the sky. Perhaps even more significant than the instruments themselves were the systematic observational programs that Islamic astronomers undertook. They recognized that ancient Greek measurements, though impressive for their time, contained errors and imprecisions that had accumulated and been perpetuated through centuries of copying and translation. The Islamic astronomers set out to create new, more accurate star catalogues through direct observation. Al-Sufi, working in the 10th century, produced a revised catalogue of stars that corrected errors in Ptolemy's ancient work and included descriptions of star brightness and colour that are still useful to historians of astronomy today. He also recorded what may be the first written description of the Andromeda galaxy, which he called a little cloud, visible to careful observers in dark skies. The measurements of planetary positions were refined through patient, repeated observations. Islamic astronomers noticed discrepancies between the predictions of Ptolemy's geocentric model and their own careful observations. Rather than simply accepting these discrepancies, they worked to develop modifications and improvements to the model. They created more complex mathematical descriptions of planetary motion, introducing additional circles and geometric constructions to better match what they saw in the sky. While they generally maintained the geocentric framework, their work represented a critical engagement with inherited knowledge, a willingness to question and improve upon the work of respected authorities. Islamic scholars also made crucial advances in mathematics that would prove essential for astronomy. They developed and refined algebra, a word that comes from the Arabic al-jabr, and made significant contributions to trigonometry, the branch of mathematics dealing with the relationships between angles and sides of triangles. Since much of astronomy involves calculating positions and distances based on angular measurements, these mathematical tools were indispensable. Astronomers could now perform more sophisticated calculations, making more accurate predictions of planetary positions and eclipse timings. The question of time itself occupied a special place in Islamic astronomy. The Islamic calendar is lunar, based on the cycles of the moon, and determining the beginning of each month requires actual observation of the thin crescent moon just after sunset. Religious obligations, particularly the 5 daily prayers, needed to be performed at specific times related to the sun's position. This practical necessity drove astronomers to develop increasingly accurate methods for determining time and the positions of celestial objects. Tables were compiled showing the times of sunrise and sunset, the direction of Mecca from various locations, and other information essential for religious observance. Astronomy was not an abstract intellectual pursuit disconnected from daily life, but an essential part of the fabric of Islamic civilization. The work of these scholars eventually flowed westward into medieval Europe through translations and through the cultural exchanges that occurred in places like Spain, where Islamic and Christian civilizations overlapped. European scholars gained access to Arabic astronomical texts, which often contained not only Islamic innovations, but also preserved Greek works that had been lost in Europe. The very names we use for many stars today reflect this heritage. Aldebaran, Rigel, Betelgeuse, Altair, and countless others are Arabic names bestowed by Islamic astronomers more than 1,000 years ago. When European scholars began to look up at the night sky with renewed curiosity during the late medieval period and the Renaissance, they built upon a foundation that Islamic astronomers had strengthened, expanded, and preserved. The astronomical achievements of the Islamic Golden Age remind us that science is not the product of any single culture or civilization, but a cumulative human endeavour, with knowledge passing from one generation and one culture to another, each adding its own insights and discoveries. The careful observations, the improved instruments, the mathematical sophistication, and the detailed records compiled by Islamic astronomers created a foundation upon which the astronomical revolution of Renaissance Europe would be built. They demonstrated that progress in understanding the cosmos required not just brilliant individual insights, but sustained programs of observation, careful instrumentation, and the institutional support that allowed astronomers to work together over many years. The questions they asked and the methods they developed would echo through the centuries that followed. In the early 16th century, a Polish mathematician and astronomer named Nicholas Copernicus began to reconsider the fundamental structure of the cosmos. For more than 1,000 years, the geocentric model of Ptolemy had reigned as the accepted description of the universe. Earth stood immobile at the centre, with the sun, moon, planets and stars revolving around it in complex patterns of circles and epicycles. The model worked reasonably well for predicting planetary positions, though it required increasingly elaborate mathematical adjustments to match observations. Copernicus found this complexity unsatisfying. He wondered whether a simpler explanation might exist, one that could account for the observed motions of the heavens with greater elegance and less mathematical contortion. The idea that Copernicus explored was not entirely new. As we have seen, the ancient Greek astronomer Aristarchus had proposed a sun-centered cosmos nearly 2,000 years earlier. But Aristarchus had been largely ignored, his idea seeming to contradict both common sense and direct observation. Copernicus, however, approached the problem with mathematical rigour and determination. He spent years working through the calculations, demonstrating that if one placed the sun at the centre of the planetary system and allowed Earth to be just another planet orbiting that central star, the apparent motions of the planets could be explained more naturally. The strange retrograde motions of the planets, those puzzling loops they traced against the background stars, were simply the result of Earth overtaking the outer planets, or being overtaken by the inner ones as all moved in their respective orbits. Copernicus compiled his ideas into a book, but he hesitated to publish it. The implications of his heliocentric model were profound and potentially dangerous. It displaced humanity from the centre of creation, suggesting that Earth was not the fixed foundation of the cosmos, but a moving world among other worlds. This challenged not only scientific tradition, but also philosophical and religious understanding. According to tradition, Copernicus received the first printed copy of his book, De Revolutionibus Orbium Coelestium, on his deathbed in 1543. Whether or not this dramatic story is entirely accurate, it is true that Copernicus was cautious about presenting his ideas to the world. The Copernican model did not immediately overturn the old geocentric system. Many astronomers found it interesting as a mathematical tool, but were reluctant to accept it as a physical reality. After all, if Earth truly moved through space, orbiting the Sun at tremendous speed, why did we not feel this motion? Why did objects fall straight down rather than being left behind by a moving Earth? Why were the stars not observed to shift their positions as Earth moved from one side of its orbit to the other? These were legitimate questions that the Copernican model, as originally formulated, could not adequately answer. The breakthrough that would eventually tip the balance came not from mathematical arguments, but from direct observation made possible by a revolutionary new instrument. In 1609, an Italian scientist named Galileo Galilei heard reports of a device invented in the Netherlands that could make distant objects appear closer. This device, which would come to be called the telescope, consisted of carefully shaped pieces of glass mounted in a tube. Galileo immediately grasped the potential of such an instrument for studying the heavens. He set about constructing his own versions, improving the design and increasing the magnification. Within a short time, he had created telescopes capable of magnifying objects 20 or even 30 times. When Galileo turned his telescope toward the night sky, he saw things that no human being had ever seen before. The moon, which appeared to the naked eye as a smooth, silvery disk, revealed itself through the telescope as a world of mountains and valleys, craters and plains. Its surface was rough and complex, not the perfect crystalline sphere that Aristotelian philosophy had decreed the heavens must be made of. He observed the sun and discovered dark spots moving across its surface, further evidence that celestial objects were not pristine and unchanging, but dynamic and material. The most consequential of Galileo's observations concerned Jupiter. Turning his telescope towards this bright planet, he noticed several small points of light arranged in a line near it. Night after night, he watched these points of light, and he realized they were changing position relative to Jupiter. They were not background stars, but objects orbiting the planet itself. Jupiter had moons, 4 of them that Galileo could see, circling their planet just as the moon circles Earth. This discovery demolished a key argument against the Copernican model. Critics had argued that if Earth moved through space, it would leave the moon behind. Yet here was Jupiter, presumably moving through space, with 4 moons faithfully accompanying it. Clearly, a moving planet could retain its satellites. Galileo observed Venus through his telescope and saw that it exhibited phases like the moon, waxing from crescent to gibbous to full and back again. This observation could only be explained if Venus orbited the Sun, passing between Earth and the Sun at some times and moving to the far side of the Sun at others. The geocentric model, with Venus orbiting Earth, could not account for the full range of phases that Galileo observed. The evidence was mounting that Copernicus had been right, that Earth and the other planets indeed revolved around the Sun. The telescope had transformed astronomy. For thousands of years, astronomers had been limited to what they could see with the naked eye. The invention of the telescope suddenly revealed a universe far richer and more complex than anyone had imagined. Galileo's relatively simple instruments, crude by modern standards, had opened a new window on the cosmos. Other astronomers quickly began building their own telescopes, each seeking to push the boundaries of what could be seen. The heavens were no longer remote and unchanging, but became a vast laboratory where new discoveries awaited anyone with a good telescope and clear skies. Yet the telescope alone did not resolve all questions about the structure of the solar system. The Copernican model, even supported by Galileo's observations, still had problems. Copernicus, like the ancient Greeks, had assumed that planetary orbits must be perfect circles. He still needed epicycles and mathematical adjustments to make his model match observations accurately. The final piece of the puzzle would come from careful analysis of the most precise naked-eye observations ever made, combined with a willingness to abandon the ancient assumption that celestial motions must be circular. That achievement would belong to Johannes Kepler, working with the extraordinary observational legacy of Tycho Brahe. But the revolution in astronomy that Copernicus initiated and Galileo's telescope advanced was already transforming humanity's understanding of its place in the cosmos. The Earth had been set in motion, and the universe had grown vastly larger and more complex than the crystalline spheres of ancient imagination. Before the telescope transformed astronomy, there lived a Danish nobleman named Tycho Brahe, who demonstrated that extraordinary precision could be achieved through careful observation with the naked eye alone. Tycho was a colourful figure, famously losing part of his nose in a duel and wearing a prosthetic replacement made of metal. But his true legacy lay not in his personal eccentricities, but in his unwavering commitment to observational accuracy. He believed that the key to understanding the heavens was measurement, precise and repeated measurement, carried out with instruments far larger and more carefully constructed than any that had come before. In 1576, King Frederick II of Denmark granted Tycho the island of Herven and funding to build an observatory. Tycho created Uraniborg, a palace of astronomy unlike anything that had existed in Europe. It was both a residence and a research facility, housing workshops for instrument makers, rooms for assistants and students, a library, and most importantly, large observing instruments mounted with extraordinary precision. Tycho designed massive quadrants and sextants, devices for measuring angles in the sky, built to such size that their graduated scales could be read with unprecedented accuracy. He developed techniques for correcting observational errors and took multiple measurements of each celestial object to ensure reliability. Night after night, year after year, Tycho and his assistants measured the positions of stars and planets. He compiled a star catalogue more accurate than any previously created, and he tracked the planets in their wandering paths across the sky with meticulous care. His observations of Mars were particularly detailed, recording its position against the background stars with an accuracy of about 1 arc minute, roughly 1/30th the diameter of the full moon. This might not sound impressive by modern standards, but it represented the absolute limit of what human eyes, aided by the best possible instruments but without optical magnification, could achieve. Tycho himself did not accept the Copernican heliocentric model. He proposed a compromise system in which the planets orbited the Sun, but the Sun itself, along with its planetary retinue, orbited a stationary Earth. This geo-heliocentric model had some attractive features and avoided certain philosophical and religious objections to Copernican theory. But Tycho's greatest contribution to astronomy was not his own model of the cosmos, but the treasure trove of observations he accumulated. These observations were so precise that they would allow the true nature of planetary motion to be discovered. That discovery came through Johannes Kepler, a German mathematician who became Tycho's assistant in the final years of the Danish astronomer's life. When Tycho died in 1601, Kepler gained access to the complete collection of observations. Kepler was a Copernican, convinced that the Sun stood at the centre of the planetary system, and he set himself the task of using Tycho's data to work out the exact nature of planetary orbits. He focused particularly on Mars, whose motion seemed especially difficult to model accurately. For years, Kepler struggled with the orbit of Mars. He tried circle after circle, adding small corrections and adjustments, attempting to find a circular path that would match Tycho's observations. Time and again, His calculations came close, but never quite matched the data. The discrepancies were small, just a few arc minutes, but Kepler trusted Tycho's observations implicitly. He knew that if his model disagreed with Tycho's measurements by even 8 arc minutes, the model must be wrong, not the observations. This was a crucial moment in the history of science. Kepler could have dismissed the small discrepancies, attributed them to observational error, and preserved the ancient belief in circular orbits. Instead, he took the data seriously and searched for a different answer. The solution, when it finally came to him, was revolutionary. The orbit of Mars was not a circle, but an ellipse, an oval shape with the Sun at one of its 2 focal points. This discovery, which Kepler published in 1609 as his first law of planetary motion, abandoned 2,000 years of astronomical tradition. The heavens were not built from perfect circles, but from ellipses. Moreover, Kepler discovered that planets did not move at constant speeds along their orbits. A planet moved faster when closer to the Sun and slower when farther away, sweeping out equal areas in equal times. This became his second law. Kepler's third law, published 10 years later, revealed a mathematical relationship between a planet's orbital period and its average distance from the Sun. These 3 laws completely describe planetary motion with elegant simplicity. No epicycles were needed, no elaborate constructions of circles upon circles. Each planet followed a single elliptical path around the Sun, and its speed varied in a predictable way. Kepler's laws worked. They predicted planetary positions with far greater accuracy than any previous model, whether geocentric or Copernican. What made Kepler's achievement possible was the combination of Tycho's extraordinarily precise observations and Kepler's willingness to follow the data wherever it led, even if it meant abandoning cherished assumptions. Kepler was driven by a mystical belief in the mathematical harmony of the cosmos. He spent much of his life searching for hidden numerical relationships and geometric patterns in the structure of the solar system. Some of these pursuits led nowhere, products of his own imagination rather than of nature. But his 3 laws of planetary motion were different. They were grounded in observation, and they revealed real patterns, mathematical relationships that actually governed the movements of the planets. Kepler's laws described how planets moved, but did not explain why they moved in these particular ways. That deeper understanding would come later, from Isaac Newton's theory of universal gravitation. But Kepler had accomplished something profound. He had shown that the complex apparent motions of the planets, which had puzzled humanity for thousands of years, could be reduced to simple mathematical laws. The universe was comprehensible. It operated according to rules that human minds could discover and express in precise mathematical form. The partnership between Tycho and Kepler, though brief and sometimes contentious, represented a crucial step in the development of modern science. Tycho demonstrated the power of precise, systematic observation. Kepler showed the importance of mathematical analysis and the willingness to question traditional assumptions when data demanded it. Together, their work transformed astronomy from a descriptive science, cataloguing the positions of celestial objects, into an analytical one, seeking the underlying laws that governed celestial motions. The revolution that Copernicus had begun was now grounded in both observational evidence and mathematical law. The stage was set for a new understanding not just of how the heavens moved, but why they moved as they did. The question of why the planets moved in their elliptical orbits, why objects fell to Earth, and what force governed the motions of celestial bodies would be answered by an English mathematician and natural philosopher whose insights would reshape humanity's understanding of the physical universe. Isaac Newton was born in 1642, the same year Galileo died, and he would build upon the work of all the astronomers and scientists who who had come before him to create a comprehensive theory of motion and gravitation that unified terrestrial and celestial physics. Newton's great insight was that the same force that caused an apple to fall from a tree also kept the moon in orbit around Earth and the planets in orbit around the sun. This was not obvious. For centuries, scholars had assumed that earthly physics and celestial physics were fundamentally different. Objects on Earth fell downward, seeking their natural place. Celestial objects moved in circles, or, as Kepler had shown, ellipses, apparently propelled by some other principle entirely. Newton demonstrated that this distinction was false. There was a single universal force of gravity that acted between all objects with mass, pulling them toward one another with a strength that depended on their masses and the distance between them. Newton expressed this gravitational force with elegant mathematical precision. The force between two objects was proportional to the product of their masses and inversely proportional to the square of the distance between them. This simple equation, the law of universal gravitation, explained an enormous range of phenomena. It explained why objects fell to Earth with accelerating speed. It explained why the moon orbited Earth rather than flying off into space or crashing into our planet. Most importantly for astronomy, when combined with Newton's laws of motion, it explained Kepler's laws of planetary motion. The elliptical orbits, the varying speeds, the mathematical relationship between orbital period and distance, all of these emerged naturally from Newton's gravitational theory. Newton published his masterwork, the Principia Mathematica, in 1687. It was written in Latin and filled with geometric proofs and mathematical reasoning of extraordinary sophistication. The Principia was not easy reading, even for educated people of Newton's time, but its impact was profound and lasting. For the first time, humanity possessed a comprehensive mathematical framework that could describe and predict the motions of objects both on Earth and in the heavens. Newton had shown that the universe operated like a vast mechanical system, governed by precise mathematical laws that could be discovered through observation and reason. The practical implications for astronomy were immediate. Astronomers could now predict planetary positions with unprecedented accuracy. They could calculate the orbits of comets, those mysterious visitors that appeared unexpectedly in the sky and had once been seen as omens or portents. Newton himself demonstrated that comets obeyed the same laws of gravitation as planets, moving in highly elongated, elliptical orbits that brought them close to the Sun at one extreme and carried them to the outer reaches of the solar system at the other. His friend Edmund Halley applied Newton's methods to historical records of comet sightings and realized that a bright comet observed in 1682 might be the same object that had appeared in 1607 and 1531. Halley predicted it would return in 1758. When the comet indeed reappeared on schedule, 16 years after Halley's death, it provided dramatic confirmation of Newtonian physics, and the comet was thereafter known as Halley's Comet. Newton's gravitational theory also revealed that the solar system was more complex than simple models suggested. The planets did not orbit the Sun in isolation, but influenced each other through their mutual gravitational attractions. Jupiter, being massive, tugged on Saturn, causing small deviations in Saturn's orbit. Earth and the Moon formed a gravitationally bound pair that together orbited the Sun. These perturbations, as they were called, were tiny but measurable, and they demonstrated that Newton's law of gravitation truly was universal, applying not just to the dominant Sun-planet interactions, but to every object pulling on every other object in the solar system. The success of Newtonian physics encouraged astronomers to make increasingly precise observations. If the theory predicted planetary positions exactly, then any deviation, no matter how small, might reveal something new. This approach led to one of the great triumphs of Newtonian astronomy. In the early 19th century, astronomers noticed that Uranus, a planet discovered in 1781 by William Herschel, was not moving exactly as Newton's laws predicted. The discrepancies were small but persistent. Two mathematicians, John Couch-Adams in England and Urbain Le Verrier in France, independently concluded that these irregularities might be caused by the gravitational influence of an as-yet undiscovered planet beyond Uranus. They calculated where such a planet should be located. In 1846, astronomer Johann Galle, using Le Verrier's predictions, pointed his telescope at the predicted position and found Neptune. It was a stunning validation of Newtonian theory. A planet had been discovered not by patient searching of the sky, but by mathematical analysis of gravitational perturbations. Yet even as Newtonian physics achieved triumph after triumph, astronomers continued to push for better instruments and more precise observations. The telescopes of Newton's time were limited by various problems. Telescopes using lenses, called refracting telescopes, suffered from chromatic aberration, a rainbow-like distortion caused by different colours of light, bending by different amounts as they passed through glass. Newton himself had invented a different type of telescope that used a curved mirror instead of a lens to gather and focus light. These reflecting telescopes avoided chromatic aberration and could be made much larger than refractors, since a large mirror could be supported from behind, while a large lens could only be supported at its edges and would sag under its own weight. Over the following centuries, telescope makers constructed ever larger reflecting telescopes. William Herschel, the discoverer of Uranus, built enormous telescopes with mirrors 4 feet across, the largest in the world during his lifetime. These great instruments gathered more light than smaller telescopes, allowing astronomers to see fainter objects. They also provided higher magnification, revealing finer details on planetary surfaces and resolving close double stars that appeared single to smaller instruments. The quest for larger telescopes became a driving force in astronomy. With each increase in size came new discoveries, new objects at the threshold of visibility, new details in familiar celestial features. The Newtonian era of astronomy was characterized by this interplay between theory and observation, between mathematical prediction and observational confirmation. Newton had provided the theoretical framework. Now astronomers set about exploring the universe it described, mapping the solar system with increasing precision, discovering new planets and moons and asteroids, measuring stellar positions and motions, and always building larger telescopes to see deeper into space. The universe was revealing itself as a place of astonishing complexity and order, governed by laws that human reason could comprehend. As telescopes grew larger and more sophisticated through the 18th and 19th centuries, astronomers began to turn their attention beyond the solar system to the stars themselves. The stars had always appeared as fixed points of light, unchanging and infinitely distant, but improved instruments revealed that the stellar realm was far more complex and dynamic than anyone had imagined. Stars had colours, subtle differences in hue that careful observers could detect. Some stars were double, appearing as single points to the naked eye, but revealing themselves through telescopes as pairs of stars orbiting one another. Other stars varied in brightness over time, pulsing brighter and dimmer in regular or irregular cycles. One of the most fundamental questions about stars concerned their distances. How far away were they? Ancient astronomers had suspected they must be enormously distant because they showed no parallax, no apparent shift in position as Earth moved from one side of its orbit to the other. If stars were relatively close, then viewing them from opposite sides of Earth's orbit, separated by nearly 200 million miles, should cause nearby stars to shift position relative to more distant background stars. Just as holding your finger at arm's length and alternately closing your left and right eye makes your finger appear to jump against the background. The absence of observable stellar parallax had been one of the arguments against a moving Earth. Copernican theory required that stars be so fantastically distant that parallax was too small to measure with naked eye observations. By the 19th century, telescopes had become precise enough to detect these minute angular shifts. In 1838, Friedrich Bessel succeeded in measuring the parallax of the star 61 Cygni. The shift was tiny, less than 1 arcsecond, an angle about the same as viewing a coin from several miles away. From this measurement, Bessel calculated that 61 Cygni lay at a distance of approximately 10 light-years, meaning that light travelling at its tremendous speed of 186,000 miles per second took 10 years to reach Earth from that star. Almost simultaneously, other astronomers measured the parallaxes and distances of other nearby stars. The stellar universe suddenly had depth and scale. The stars were not fixed to a celestial sphere just beyond the planets, but scattered through vast reaches of space. Understanding the nature of light itself became crucial to astronomy during this period. Newton had believed light consisted of particles, tiny corpuscles emitted by luminous objects, but experiments in the early 19th century demonstrated that light behaved as a wave, exhibiting interference and diffraction patterns that only waves could produce. If light was a wave, what was waving? The answer came from James Clerk Maxwell, who showed mathematically that light was an electromagnetic wave, a self-propagating oscillation of electric and magnetic fields that could travel through empty space. This understanding opened new possibilities for astronomy because different types of electromagnetic radiation, from radio waves to X-rays, might reveal different aspects of celestial objects. One of the most powerful tools to emerge from understanding light was spectroscopy, the analysis of light broken into its component colours. When light from the sun or a star passed through a prism or diffraction grating, it spread into a rainbow spectrum, but this spectrum was not smooth and continuous. It was crossed by dark lines at specific wavelengths. These spectral lines, first observed in detail by Joseph von Fraunhofer in the early 19th century, were fingerprints of chemical elements. Each element absorbed or emitted light at characteristic wavelengths, creating a unique pattern of lines. By studying the spectrum of sunlight or starlight, astronomers could determine what elements existed in the sun or star, even though those objects were impossibly far away. Spectroscopy transformed astronomy from a science of positions and motions into a science that could investigate the physical nature and composition of celestial objects. Astronomers discovered that the sun contained hydrogen, helium, iron, and many other elements. Stars, though their light appeared simply white or perhaps slightly coloured to the eye, revealed themselves through spectroscopy to have diverse compositions and temperatures. Hot blue stars showed different spectral patterns than cooler red stars. Some stars showed strong hydrogen lines, while others showed lines of metals. Astronomers began to classify stars into categories based on their spectra, creating an organizational system that revealed underlying patterns in stellar properties. Another remarkable discovery emerged from spectroscopy. When astronomers measured the wavelengths of spectral lines from stars, they sometimes found that the entire pattern of lines was shifted slightly toward either the blue or red end of the spectrum compared to light from laboratory sources. This shift could be explained by the Doppler effect, the same phenomenon that causes the pitch of a siren to change as an ambulance speeds past. If a star was moving toward Earth, its light waves would be compressed, shifting spectral lines toward shorter, bluer wavelengths. If moving away, the waves would be stretched, shifting lines toward longer, redder wavelengths. By measuring these shifts, astronomers could determine the radial velocity of stars, how fast they were moving toward or away from Earth. These velocity measurements revealed that stars were not fixed in place, but moved through space with various speeds and directions. The Sun itself was moving, carrying the solar system through the Milky Way. Some stars showed periodic velocity variations, speeding up and slowing down on regular schedules. These variations often indicated the presence of a companion star too faint or too close to see directly. The two stars orbited their common center of mass, and as they did so, sometimes one star approached Earth while the other receded, then reversed, causing the observed velocity oscillations. Spectroscopy had given astronomers a way to detect invisible companions and to map the motions of stars throughout the galaxy. Photography added another revolutionary capability to astronomy. In the mid-19th century, astronomers began attaching cameras to telescopes, capturing images on photographic plates instead of relying solely on visual observation through the eyepiece. Photographic plates had several advantages. They could accumulate light over long exposures, revealing faint objects invisible to the eye during brief glances. They provided permanent records that could be studied at leisure, measured precisely, and compared with photographs taken years later to detect motions or changes. Photographic surveys of the sky recorded the positions and brightnesses of millions of stars, creating comprehensive catalogues that would have been impossible through visual observation alone. The combination of large telescopes, spectroscopy, photography, and precise measurement techniques gave 19th century astronomers tools of unprecedented power. They could determine not just where celestial objects were, but what they were made of, how fast they moved, how hot they burned, and how they compared to one another. Astronomy was becoming astrophysics, a science concerned not merely with describing the heavens, but with understanding the physical processes that governed them. The stars were no longer distant, enigmatic lights, but became objects that could be studied, analysed, and gradually understood through the application of physics and chemistry. Each new technique and instrument revealed another layer of complexity in the cosmos. By the early 20th century, astronomers had accumulated vast amounts of data about stars, their spectra, their brightnesses, and their motions, but they still lacked answers to fundamental questions. What powered the stars, allowing them to shine for what appeared to be enormous spans of time? How large were stars compared to the Sun? How were stars born, and did they eventually die? The answers to these questions would emerge through careful analysis of the data astronomers had gathered and through revolutionary new understandings of physics that developed in the early decades of the century. One crucial breakthrough came from understanding the relationship between a star's temperature and its luminosity. Around 1900, astronomers began plotting stars on diagrams with temperature on one axis and brightness on the other. When Einar Hertzsprung in Denmark and Henry Norris Russell in America independently created such diagrams, they discovered that stars did not scatter randomly across the plot, but fell into distinct patterns. Most stars lay along a diagonal band called the main sequence, running from hot, luminous blue stars to cool, dim red stars. The Sun sat roughly in the middle of this main sequence, but some stars fell in other regions of the diagram. Some were cool yet extremely luminous, which meant they must be enormous in size to emit so much light despite their low surface temperatures. These became known as red giants. Others were hot but dim, indicating they were tiny, and these were called white dwarfs. The Hertzsprung-Russell diagram, as it came to be known, was more than just an organizational tool. It hinted at stellar evolution, the idea that stars changed over time, perhaps beginning their lives in one region of the diagram and migrating to other regions as they aged. But understanding this evolution required knowing what made stars shine in the first place, and that understanding would come from the new physics of the 20th century. Albert Einstein's famous equation, E equals mc squared, announced in 1905, revealed that mass and energy were interchangeable. A small amount of mass could be converted into an enormous amount of energy. This suggested a possible power source for stars. If somehow the nuclei of atoms could be fused together, combining lighter elements into heavier ones, the small loss of mass in the process would be converted to energy according to Einstein's equation. In the late 1920s and 1930s, physicists worked out the details of how such nuclear fusion could occur in the extreme conditions at the centres of stars, where temperatures reached millions of degrees and pressures were immense. The Sun, it turned out, was powered by the fusion of hydrogen into helium. Deep in the solar core, hydrogen nuclei collided with such energy that they overcame their natural electrical repulsion and merged, forming helium nuclei. The helium nucleus weighed slightly less than the 4 hydrogen nuclei that formed it, and this missing mass was converted to energy that eventually made its way to the Sun's surface and radiated into space as sunlight. This process could sustain the Sun's luminosity for billions of years, solving the long-standing puzzle of stellar longevity. Understanding nuclear fusion allowed astronomers to construct theoretical models of stellar structure and evolution. A star's life was determined largely by its mass. Massive stars burned through their hydrogen fuel quickly, living brief but brilliant lives of perhaps only millions of years. They shone with tremendous luminosity, appearing as the hot blue stars on the main sequence. Smaller stars like the Sun burned their fuel more slowly and could shine steadily for billions of years. The least massive stars, cool red dwarfs, were so miserly with their fuel that they could shine for trillions of years, longer than the current age of the universe. When a star exhausted the hydrogen in its core, its structure changed dramatically. The core contracted and heated, while the outer layers expanded and cooled. The star moved off the main sequence and became a red giant, swelling to enormous size. For a star like the Sun, this red giant phase would eventually consume the inner planets, possibly including Earth, as the Sun's outer layers expanded beyond the orbit of Venus. In the cores of red giants, new fusion reactions began, converting helium into carbon and oxygen. More massive stars could ignite even heavier fusion reactions, building elements up the periodic table toward iron. The end of a star's life depended on its mass. Stars like the Sun would eventually shed their outer layers as glowing shells of gas called planetary nebulae, leaving behind the collapsed core as a white dwarf, a dense ember slowly cooling over billions of years. More massive stars met more violent ends. When they exhausted all possible fusion reactions, their cores collapsed catastrophically, and the outer layers exploded in a supernova, briefly outshining entire galaxies. These explosions scattered heavy elements into space, enriching the interstellar medium with carbon, oxygen, silicon, iron, and all the other elements forged in stellar cores. The supernova remnants could collapse to form neutron stars, objects so dense that a teaspoonful would weigh as much as a mountain, or even black holes, regions where gravity was so intense that nothing, not even light, could escape. This understanding of stellar evolution provided a cosmic context for human existence. The heavy elements that made up Earth and everything on it, including the atoms in human bodies, had been forged in the cores of ancient stars that exploded billions of years ago. We were, in a very real sense, made of stardust, the remnants of stellar alchemy scattered across the galaxy and eventually incorporated into a new generation of stars and planets. During the same period that stellar physics was being worked out, telescopes continued to grow larger. The early 20th century saw the construction of truly enormous instruments. The Mount Wilson Observatory in California housed a 60-inch reflecting telescope completed in 1908, followed by the 100-inch Hooker telescope in 1917. This latter instrument remained the world's largest telescope for decades, and it was with this telescope that some of the most profound astronomical discoveries of the 20th century would be made. The larger telescopes revealed more of the universe's structure. Astronomers could see fainter stars, more distant clusters, and mysterious fuzzy patches of light called nebulae. Some nebulae were clearly clouds of gas illuminated by nearby stars. Others had a different character entirely, showing spiral or elliptical structures that suggested they might be vast systems of stars. The question of whether these spiral nebulae lay within our Milky Way galaxy or were separate galaxies far beyond it became one of the great debates of early 20th century astronomy, a debate that would be resolved through careful observation and a special type of variable star that would serve as a cosmic measuring rod. The debate over the nature of spiral nebulae reached its resolution through the work of Henrietta Leavitt and Edwin Hubble, though the path to understanding required several crucial steps. Leavitt worked at the Harvard College Observatory in the early 1900s, examining photographic plates of the Magellanic Clouds, two fuzzy patches visible in southern hemisphere skies. Within these clouds, she identified variable stars called Cepheids, named after the star Delta Cephei, which brightened and dimmed in regular cycles. What Leavitt discovered was remarkable. The brighter a Cepheid was at its maximum luminosity, the longer its period of variation. A Cepheid that pulsed over 10 days was intrinsically more luminous than one that pulsed over 3 days. This period luminosity relationship was extraordinarily valuable because it provided a way to measure cosmic distances. If astronomers could identify a Cepheid variable in a distant object and measure its period, they could determine its intrinsic luminosity. By comparing this intrinsic luminosity to how bright the star appeared from Earth, they could calculate its distance. It was like seeing a light bulb in the distance and knowing its wattage. By how dim it appeared, you could determine how far away it must be. Cepheid variables became cosmic distance markers, standard candles by which the scale of the universe could be measured. Edwin Hubble used the 100-inch telescope at Mount Wilson to search for Cepheid variables in spiral nebulae. In 1923, he found them in the Andromeda Nebula, that faint smudge of light visible to the naked eye on clear autumn nights. By measuring the periods of these Cepheids and applying Leavitt's relationship, Hubble calculated that Andromeda lay at a distance of roughly 900,000 light-years. This was far beyond any distance within our own Milky Way galaxy. Andromeda was not a nebula at all, but a separate galaxy, an enormous collection of stars comparable in size to our own galaxy, but separated from it by vast reaches of empty space. The universe suddenly expanded in human imagination. The Milky Way, which had seemed to encompass all of creation, was just one galaxy among multitudes. Hubble and other astronomers identified more and more galaxies scattered throughout space in all directions. Some were spirals like Andromeda, with graceful arms winding outward from a bright central nucleus. Others were elliptical, shaped like footballs or spheres with no spiral structure. Still others were irregular, lacking any organized form. Each galaxy contained billions or even hundreds of billions of stars. The universe was unimaginably larger than anyone had conceived, but Hubble's discoveries did not end with establishing the existence of other galaxies. He continued studying their properties, particularly their motions. Using spectroscopy, Hubble measured the redshifts of galaxies, determining how fast they were receding from Earth based on how much their spectral lines were shifted toward longer wavelengths. What he found, announced in 1929, was astonishing. Nearly all galaxies showed redshifts, meaning they were moving away from us. More remarkably, the farther away a galaxy was, the faster it appeared to be receding. This relationship between distance and recession velocity became known as Hubble's law. The implications were profound. If all galaxies were moving away from each other, the universe itself must be expanding, with space itself stretching and carrying galaxies along with it. This was not an explosion in space, but an expansion of space. Imagine dots painted on the surface of a balloon. As the balloon inflates, all the dots move away from each other, not because they're travelling across the balloon's surface, but because the surface itself is expanding. Hubble's observations suggested the universe behaved similarly. If the universe was expanding now, then in the past it must have been smaller and denser. Tracing this expansion backward in time led to a startling conclusion. The universe appeared to have begun in an extremely hot, dense state, and had been expanding and cooling ever since. This idea, later called the Big Bang Theory, revolutionized cosmology. The universe had not existed eternally in a static state, but had a beginning, a moment of origin some finite time in the past. The Big Bang Theory made predictions that could be tested. If the universe began in a hot, dense state, there should be remnant radiation from that early epoch, cooled by the expansion of the universe, but still detectable. In 1964, Arno Penzias and Robert Wilson, working with a radio antenna at Bell Laboratories, detected a faint microwave signal coming from all directions in the sky. This cosmic microwave background radiation, as it came to be called, was the cooled remnant of the Big Bang itself, light that had travelled through space for nearly 14 billion years. Its discovery provided strong confirmation of the Big Bang Theory and gave cosmologists a powerful tool for studying the early universe. Radio astronomy, which detected the cosmic microwave background, had emerged as a new branch of astronomy in the decades following World War II. Radio waves are a form of electromagnetic radiation with much longer wavelengths than visible light, and they could reveal aspects of the universe invisible to optical telescopes. The technology developed for radar during the war was adapted for astronomical purposes, and radio telescopes began scanning the skies. They discovered radio emission from Jupiter, from the Sun's corona, from the Milky Way's centre, and from distant galaxies. Some galaxies emitted far more energy in radio wavelengths than in visible light, suggesting violent processes at work in their cores. Radio telescopes looked quite different from their optical counterparts. Instead of mirrors or lenses, they used large metal dishes to collect and focus radio waves. The dishes could be enormous because radio wavelengths were long and did not require the same precision of surface as optical mirrors. The Arecibo radio telescope in Puerto Rico, completed in 1963, used a natural bowl-shaped valley to support a dish 1,000 feet across. Radio telescopes could observe day or night, and could peer through dust clouds that blocked visible light, revealing the structure of the Milky Way's spiral arms and detecting objects hidden from optical view. One of the most mysterious discoveries of radio astronomy came in 1967 when Jocelyn Bell, a graduate student working with Anthony Hewish at Cambridge University, noticed peculiar signals in radio data. The signals were incredibly regular pulses of radio emission, arriving precisely every 1.3 seconds. At first, the team wondered whether they might have detected signals from an extraterrestrial civilization. but further observations revealed other pulsing sources with different periods. These objects, called pulsars, turned out to be rapidly spinning neutron stars, the collapsed cores left behind after supernova explosions. As the neutron star rotated, beams of radio emission swept across space like lighthouse beams, producing the regular pulses detected on Earth. The universe revealed through radio astronomy was far more dynamic and energetic than the serene view provided by optical telescopes. Galaxies collided and merged. Supermassive black holes lurked at galactic centers, devouring matter and producing jets of particles that streamed outward at nearly the speed of light. The cosmos was not a peaceful, unchanging realm, but a place of violence and transformation, of continuous creation and destruction unfolding across billions of years. As the 20th century progressed, astronomers realized that observing the universe only in visible light and radio waves was like listening to an orchestra with cotton in your ears. Visible light represented just a narrow slice of the electromagnetic spectrum, and many cosmic phenomena radiated most of their energy at wavelengths the human eye could not see. X-rays, ultraviolet light, infrared radiation, and gamma rays all carried information about the universe. But Earth's atmosphere blocked most of these wavelengths from reaching ground-based telescopes. To observe the universe across the full electromagnetic spectrum, telescopes would need to be lifted above the atmosphere into the vacuum of space itself. The space age began in 1957 with the Soviet launch of Sputnik, and it quickly became apparent that satellites and spacecraft offered revolutionary opportunities for astronomy. The first astronomical satellites were modest instruments, but they immediately revealed phenomena invisible from Earth's surface. Rockets carrying X-ray detectors discovered that the Sun emitted X-rays from its corona, the superheated outer atmosphere visible during solar eclipses. They found X-ray sources beyond the solar system, mysterious objects emitting tremendous energy in this high-frequency radiation. One particularly intriguing X-ray source, discovered in 1964 and called Cygnus X1, appeared to be a binary system where a visible blue supergiant star orbited an invisible companion. The X-rays seemed to come from the invisible companion, and calculations suggested this object was far too massive to be a white dwarf or even a neutron star. Astronomers concluded they might be observing a black hole, a region of space where gravity was so intense that nothing could escape, not even light. Matter from the visible star was being pulled toward the black hole, forming a swirling disk of superheated gas that emitted X-rays before crossing the point of no return. Black holes, which had been predicted theoretically from Einstein's general relativity but seemed almost too strange to be real, appeared to actually exist in nature. Infrared astronomy revealed another hidden universe. Infrared radiation, with wavelengths longer than visible light, is emitted by warm objects that are not hot enough to glow visibly. Many celestial objects and phenomena radiate primarily in the infrared. Dust clouds that blocked visible light were transparent to infrared, allowing astronomers to peer into stellar nurseries where new stars were forming. Cool stars and planets that emitted little visible light shone brightly in infrared wavelengths. Even the cosmic microwave background, when mapped precisely, showed tiny temperature variations that revealed the seeds of structure in the early universe. Slight density differences that would eventually grow into galaxies and clusters of galaxies. The Hubble Space Telescope, launched in 1990, became perhaps the most famous and scientifically productive space observatory ever built. Named after Edwin Hubble, this instrument carried a mirror 94 inches in diameter above Earth's atmosphere, where it could observe without atmospheric distortion or light pollution. The images Hubble transmitted to Earth were breathtaking in their clarity and beauty. It photographed galaxies colliding, stars being born in glowing nebulae, and the intricate structures of dying stars shedding their outer layers. Hubble's deep field images, made by pointing the telescope at seemingly empty patches of sky and collecting light for days, revealed thousands of galaxies in every direction, demonstrating that the universe was filled with galaxies as far as the telescope could see. Hubble made crucial measurements that refined our understanding of the universe's expansion. By observing distant supernovae, a particular type called type Ia, that served as standard candles, similar to Cepheid variables but visible across much greater distances, Hubble helped astronomers measure the expansion rate of the universe with unprecedented precision. These observations led to a shocking discovery, announced in 1998. The expansion of the universe was not slowing down as gravity pulled galaxies back toward each other, as had been expected. Instead, the expansion was accelerating. Some mysterious force, dubbed dark energy, was pushing the universe to expand faster and faster. This dark energy appeared to make up about 70% of all the energy in the universe, yet its nature remained completely unknown. It was perhaps the deepest mystery in modern cosmology. Other space telescopes specialized in different wavelengths. The Chandra X-ray Observatory, launched in 1999, studied X-ray emissions from black holes, supernova remnants, and galaxy clusters. The Spitzer Space Telescope observed in infrared, mapping the structure of the Milky Way and studying planets forming around distant stars. Each observatory added pieces to the cosmic puzzle, revealing aspects of the universe that had been hidden or unknown. Ground-based telescopes also continued to advance. New technologies allowed astronomers to partially compensate for atmospheric distortion through a technique called adaptive optics. Rapidly adjustable mirrors could change shape hundreds of times per second, correcting for the blurring effects of turbulent air. With adaptive optics, ground-based telescopes could achieve image sharpness rivaling space telescopes, at least for short wavelengths of infrared light where the technique worked best. Observatories constructed enormous telescopes with mirrors segments fitted together to create collecting areas much larger than any single mirror that could be manufactured. The twin Keck telescopes in Hawaii, each with a primary mirror 33 feet across, made of 36 hexagonal segments, became operational in the 1990s and represented the state-of-the-art in ground-based observing. The combination of space-based and ground-based observatories, working across the electromagnetic spectrum, transformed astronomy once again. Questions that had seemed unanswerable became accessible to observation. How common were planets around other stars? Do planets form in the same way everywhere, or are there exotic configurations impossible in our own solar system? What were the earliest galaxies like, and how did they evolve into the galaxies we see today? Are there Earth-like planets in the habitable zones of other stars, where liquid water might exist on planetary surfaces? The late 20th and early 21st centuries saw an explosion of discoveries, as these powerful instruments were brought to bear on fundamental questions. Thousands of planets were discovered orbiting other stars, some similar to Earth and some wildly different, gas giants larger than Jupiter, orbiting closer to their stars than Mercury orbits the Sun, or rocky planets circling multiple stars in complex gravitational dances. Astronomers mapped the large-scale structure of the universe, finding that galaxies were not scattered randomly, but arranged in vast filaments and sheets surrounding enormous voids, creating a cosmic web stretching across billions of light years. They detected gravitational waves, ripples in space-time itself, produced by colliding black holes and neutron stars, opening an entirely new window for observing the universe. not through electromagnetic radiation, but through the fabric of space itself. Among the most profound questions that humanity has asked is whether we are alone in the universe. The discovery of thousands of planets orbiting other stars has transformed this ancient question from philosophical speculation into a subject of scientific investigation. The search for exoplanets, as planets beyond our solar system are called, represents one of the great detective stories of modern astronomy, requiring ingenious techniques to detect worlds trillions of miles away that emit no light of their own and are lost in the glare of their parent stars. The first confirmed detection of a planet orbiting a Sun-like star came in 1995, when Michel Maire and Didier Queloz announced the discovery of a planet around the star 51 Pegasi. They detected this planet not by seeing it directly, but by observing the subtle wobble it induced in its star. As a planet orbits a star, the star itself moves slightly, pulled by the planet's gravity into a small orbit around the system's common centre of mass. This motion causes the star's light to shift back and forth in wavelength due to the Doppler effect, the same phenomenon that allows astronomers to measure stellar velocities. By detecting these periodic shifts in the star's spectrum, Maire and Queloz inferred the presence of a planet roughly half the mass of Jupiter orbiting extremely close to its star, completing one orbit every 4 days. This discovery was surprising because the planet, later called a hot Jupiter, was unlike anything in our solar system. Giant planets in our system orbit far from the Sun where temperatures are cold enough for hydrogen and helium to condense. A Jupiter-mass planet orbiting closer to its star than Mercury orbits the Sun challenged existing theories of planet formation. Yet as more exoplanets were discovered, hot Jupiters proved to be relatively common. The universe apparently produced planetary systems in configurations we had never imagined. Another technique for finding exoplanets emerged from precise monitoring of stellar brightness. If a planet's orbit happens to carry it directly between its star and Earth, the planet will block a tiny fraction of the star's light during each transit, causing a periodic dimming. These brightness changes are minute, typically less than 1%, but modern detectors can measure them. The Kepler Space Telescope, launched in 2009, used this transit method to monitor more than 150,000 stars simultaneously, searching for the telltale periodic dips that would betray the presence of orbiting planets. Kepler's discoveries revolutionized our understanding of planetary systems. It found thousands of planets, ranging from gas giants larger than Jupiter to rocky worlds smaller than Earth. It discovered systems where multiple planets orbited in tight formation, passing within fractions of an astronomical unit of each other. It found planets in the habitable zones of their stars, that range of distances where temperatures might allow liquid water to exist on a planet's surface. Some stars hosted 7 or 8 known planets, complex systems reminiscent of our own solar system, but arranged in unfamiliar configurations. Statistical analysis of Kepler's results suggested that planets are remarkably common. Nearly every star in the galaxy likely hosts at least one planet, and many have multiple worlds. Earth-sized rocky planets appear particularly abundant. Some calculations suggest there might be billions of Earth-sized planets in the habitable zones of stars within our galaxy alone. Whether any of these worlds actually harbour life remains unknown, but the sheer number of potentially habitable environments suggests that the conditions necessary for life might arise frequently throughout the cosmos. Detecting exoplanets is only the first step toward understanding them. Astronomers have developed techniques to study the atmospheres of these distant worlds by analysing starlight that passes through or reflects off planetary atmospheres during transits. Different molecules absorb light at characteristic wavelengths, creating spectral signatures that can be detected even across interstellar distances. Water vapour, methane, carbon dioxide and other gases have been identified in the atmospheres of giant exoplanets. As telescopes and techniques improve, similar studies of smaller, more Earth-like planets are becoming possible. The James Webb Space Telescope, launched in 2021, represents the next generation of space observatory. With a mirror more than 21 feet across and instruments optimized for infrared observations, Webb can detect the faint heat signatures of planets and study their atmospheres in unprecedented detail. It can observe the most distant galaxies, seeing them as they appeared when the universe was only a few 100 million years old, shortly after the first stars ignited. Webb's infrared vision allows it to peer through dust clouds that block visible light, revealing stellar nurseries and the hearts of galaxies. Early results from Webb have already challenged some assumptions about galaxy formation, finding surprisingly massive and well-developed galaxies at times when the universe was supposed to be in its infancy. The search for life beyond Earth has also extended into our own solar system. Mars, once thought to be a frozen desert with no prospect of harbouring life, has revealed evidence of a watery past. Robotic rovers have found ancient lake beds, minerals that form in the presence of water, and complex organic molecules preserved in Martian rocks. While these discoveries do not prove that life ever existed on Mars, they demonstrate that the planet once had conditions that, on Earth, would have been suitable for life. Future missions plan to return samples of Martian rock to Earth for detailed laboratory analysis, searching for any chemical or structural evidence of past microbial life. The icy moons of the outer solar system have emerged as particularly intriguing targets in the search for life. Europa, a moon of Jupiter, has a thick ice shell covering a global ocean of liquid water, kept warm by tidal heating from Jupiter's immense gravity. Enceladus, a small moon of Saturn, shoots geysers of water into space from cracks in its icy surface, revealing a subsurface ocean beneath. These hidden oceans, shielded from space radiation by thick ice, might provide habitable environments for simple life forms. Missions are being planned to fly through the geysers of Enceladus or drill through Europa's ice, searching for any signs of biology in these alien seas. The discovery that life's basic chemical building blocks, including amino acids and complex organic molecules, exist naturally in space has reinforced the possibility that life might arise wherever conditions permit. Meteorites have delivered organic compounds to Earth throughout the planet's history, and similar processes operate throughout the galaxy. The raw materials for life appear to be common. Whether the spark that transforms chemistry into biology is equally common, or whether Earth's biosphere represents a unique or rare occurrence remains one of the great unanswered questions. But astronomy has brought us closer than ever to finding an answer. Throughout the history of astronomy, each new instrument and technique has revealed layers of complexity in the universe that previous generations could not have imagined. The late 20th and early 21st centuries brought discoveries that challenged our understanding of the cosmos at its most fundamental level. Among the most perplexing of these discoveries was the realization that the matter we can see, the atoms that make up stars and planets and galaxies, represents only a small fraction of all the matter that exists. The first hints of this invisible matter came from studying the rotation of galaxies. In the 1970s, astronomer Vera Rubin conducted careful measurements of how fast stars orbit within spiral galaxies. According to Newton's laws, stars farther from a galaxy's centre should orbit more slowly, just as the outer planets in our solar system orbit more slowly than the inner ones. But Rubin's observations showed something entirely different. Stars in the outer regions of galaxies move just as fast as those closer to the centre, sometimes even faster. The only way to explain these high orbital speeds was to assume that galaxies contained far more mass than could be accounted for by their visible stars and gas. This invisible mass became known as dark matter. It does not emit, absorb or reflect light, making it completely invisible to telescopes observing any wavelength of electromagnetic radiation. Its presence can only be inferred through its gravitational effects on visible matter. Computer simulations of galaxy formation showed that without dark matter, galaxies as we observe them could not exist. The dark matter provides the gravitational scaffolding around which normal matter collects, forming the galaxies and clusters of galaxies we see. Current estimates suggest that dark matter outweighs ordinary matter by a factor of about 5 to 1. The universe is dominated by a substance we cannot see and whose nature remains unknown. Various theories have been proposed for what dark matter might be. It could consist of exotic subatomic particles that interact only through gravity and perhaps the weak nuclear force, moving through space and through ordinary matter as though they were ghosts. Experiments deep underground and in space have searched for these hypothetical particles, trying to detect the rare occasions when one might interact with ordinary matter, but so far no conclusive detection has been made. Another possibility is that dark matter consists of massive compact objects, like black holes or failed stars, but astronomical surveys have largely ruled out this explanation for most of the missing mass. Even more mysterious than dark matter is dark energy, the force that appears to be accelerating the expansion of the universe. The discovery of cosmic acceleration came from observations of distant Type Ia supernovae, stellar explosions so bright they can be seen across billions of light years. These supernovae serve as standard candles because they all reach approximately the same peak brightness. By comparing how bright they appear to how bright they should be based on their redshift and distance, astronomers can test whether the universe's expansion has been constant, speeding up, or slowing down over cosmic history. The results, announced by two independent teams in 1998, were completely unexpected. The distant supernovae appeared fainter than predicted, meaning they were farther away than expected. The universe's expansion had been accelerating for the past several billion years, pushed apart by some unknown form of energy permeating all of space. This dark energy does not dilute as space expands, but maintains a constant density, meaning that as the universe grows larger, the total amount of dark energy increases. It currently makes up about 70% of all the energy in the universe, yet physicists have no idea what it is or why it exists. One possibility is that dark energy represents the energy of empty space itself, what quantum physics calls the vacuum energy. According to quantum theory, even empty space is not truly empty, but seethes with virtual particles constantly popping into and out of existence. This quantum vacuum should have energy, and that energy would push space apart in exactly the way dark energy appears to do. However, when physicists calculate how much vacuum energy quantum theory predicts, they get a number that is vastly larger than the observed dark energy density, off by a factor of 10 to the power of 120, perhaps the worst prediction in the history of physics. This enormous discrepancy suggests that our understanding of either quantum physics, gravity, or both is incomplete. The nature of dark matter and dark energy represents perhaps the deepest mystery in contemporary physics and cosmology. We have detailed maps of the cosmic microwave background radiation, precise measurements of the universe's expansion rate, and sophisticated computer simulations of cosmic structure formation. Yet we must admit that we do not understand what constitutes 95% of the universe. The atoms that make up everything we can see and touch All the stars and planets and galaxies are merely a small component floating in an ocean of invisible matter and energy. Despite these profound mysteries, astronomers have constructed a remarkably detailed history of the universe from its beginning to the present. The universe began approximately 13.8 billion years ago in an extremely hot, dense state. In the first fraction of a second, it underwent a period of exponential expansion called inflation, growing from submicroscopic to macroscopic size almost instantaneously. As the universe expanded and cooled, fundamental particles condensed out of the energy, then combined to form the first atomic nuclei. After several 100,000 years of further expansion, the universe cooled enough for electrons to combine with nuclei, forming neutral atoms. At this moment, light could travel freely through space for the first time, and this ancient light, stretched by billions of years of cosmic expansion, is what we detect today as the cosmic microwave background radiation. For hundreds of millions of years after this epoch, the universe was dark, filled with neutral hydrogen gas, but no stars. Then gradually, the first stars ignited, massive brilliant objects that lived brief, violent lives and died in supernova explosions, enriching space with heavier elements. These first stars clustered together under gravity's pull, forming the first galaxies. Galaxies merged and grew, developing the structures we observe today. Throughout this cosmic evolution, dark matter provided the gravitational framework, while dark energy, though negligible in the early universe, gradually came to dominate and is now driving galaxies apart at ever-increasing speeds. Looking to the future, astronomers project that the universe's expansion will continue accelerating. Distant galaxies will recede beyond the cosmic horizon, their light redshifted into invisibility. Eventually, billions of years hence, only our local group of gravitationally bound galaxies will remain visible, isolated in an ever-expanding sea of space. Stars will continue forming for trillions of years, but eventually the raw materials for star formation will be exhausted. The universe will grow cold and dark, populated only by the slowly cooling remnants of dead stars and the evaporating remains of black holes. This far future seems bleak, yet it is also humbling to realize that we live in a cosmic epoch where the universe is still young, still vibrant, still filled with light. The technological evolution of astronomical instruments has been a story of gathering light, of building ever more sensitive devices to capture the faint whispers arriving from across vast cosmic distances. Each photon that reaches Earth from a distant galaxy has travelled for millions or billions of years, carrying information about its source encoded in its wavelength and energy. The history of observational astronomy is largely the history of inventing better ways to collect and analyse these precious messengers from space. The earliest telescopes, built by Galileo and his contemporaries in the early 1600s, used simple glass lenses to bend and focus light. These refracting telescopes suffered from a problem called chromatic aberration, where different colours of light focused at slightly different points, creating rainbow-coloured halos around bright objects. Isaac Newton solved this problem by inventing the reflecting telescope, which used a curved mirror instead of a lens to gather light. Mirrors could be made much larger than lenses, and they did not suffer from chromatic aberration. Nearly all major astronomical telescopes today are reflectors, descendants of Newton's design though vastly improved in sophistication and scale. The quest for larger mirrors has driven telescope construction for centuries. A larger mirror collects more light, allowing fainter objects to be detected, and it also provides better resolution, the ability to distinguish fine details or separate close objects. William Herschel, working in the late 1700s, constructed telescopes with mirrors up to 4 feet in diameter, the largest of his era. These giant instruments were unwieldy, requiring elaborate scaffolding and supports, but they revealed unprecedented details of nebulae and star clusters and led to Herschel's discovery of the planet Uranus. Through the 19th and 20th centuries, telescope mirrors grew progressively larger. The challenge was not just making big mirrors, but making them precisely curved and supporting them so they did not sag under their own weight. A telescope mirror must maintain its shape to within a fraction of a wavelength of light, an accuracy measured in millionths of an inch, or the image quality will be degraded. Larger mirrors are heavier and more prone to distortion from gravity and temperature changes. Engineers developed ingenious support systems with dozens or hundreds of actuators that could push and pull on the back of the mirror, continuously adjusting its shape to compensate for these distortions. Modern large telescopes use segmented mirrors, where the primary mirror is not a single piece of glass, but an assembly of hexagonal segments fitted together like tiles. Each segment can be individually positioned and shaped by computer-controlled actuators. The two Keck telescopes, completed in the early 1990s, pioneered this approach with mirrors composed of 36 segments, creating a total collecting area equivalent to a single mirror 33 feet across. This segmented design allows mirrors to be made much larger than would be possible with a single piece of glass. The largest optical telescopes currently in operation or under construction use mirrors 30 feet to more than 130 feet in diameter. The European Extremely Large Telescope, under construction in Chile, will have a segmented primary mirror 130 feet across, composed of 798 individual segments. When completed, it will gather 13 times more light than the largest telescopes operating today and will be capable of directly imaging planets around nearby stars and studying the atmospheres of those worlds for signs of biological activity. Location matters almost as much as size for ground-based telescopes. Earth's atmosphere blurs and distorts starlight, causing stars to twinkle and limiting the sharpness of telescope images. The best observatory sites are on high mountains in dry climates where the air is thin, stable, and free from moisture and dust. Mountain peaks in Chile, Hawaii, and the Canary Islands host many of the world's premier observatories, chosen for their exceptionally clear and steady skies. Even at these excellent sites, atmospheric turbulence limits image quality, which is why adaptive optics systems have become essential. These systems use deformable mirrors that change shape hundreds or thousands of times per second, correcting for atmospheric distortion and allowing ground-based telescopes to achieve image sharpness comparable to space telescopes. Radio telescopes face different challenges than optical instruments. Radio waves have much longer wavelengths than visible light, which means radio telescopes naturally have poorer resolution. To achieve sharp images, radio telescopes must be enormous, or more commonly, multiple radio telescopes must be combined in arrays, with their signals electronically joined to simulate a single telescope as large as the distance between the individual dishes. The Very Large Array in New Mexico consists of 27 radio dishes arranged along railroad tracks in a Y-shaped configuration. The dishes can be moved to different positions, allowing the array to be reconfigured for different observing projects. When the dishes are spread across their maximum 22-mile extent, the array achieves resolution comparable to optical telescopes, despite observing at much longer wavelengths. Radio interferometry has been extended to truly extraordinary scales through very long baseline interferometry, where radio telescopes on different continents combine their observations. The Event Horizon Telescope, a collaboration of radio observatories around the world, used this technique to create the first image of a black hole's shadow in 2019. The supermassive black hole at the center of the galaxy, Messier 87, located 55 million light-years away, was imaged with enough resolution to see the silhouette of the black hole against the glowing disk of material swirling around it. This achievement required synchronizing observations from telescopes in Chile, Hawaii, Arizona, Mexico, Spain, and Antarctica, effectively creating a telescope as large as the Earth itself. Gravitational wave detectors represent an entirely new class of astronomical instrument, observing the universe not through electromagnetic radiation, but through ripples in space-time itself. The laser interferometer. Gravitational Wave Observatory, known as LIGO, consists of two facilities in Louisiana and Washington state, each with two perpendicular arms, 2.5 miles long. Laser beams bounce back and forth along these arms, and when a gravitational wave passes through Earth, it stretches space in one direction while compressing it in the perpendicular direction. These distortions are fantastically small, changing the length of LIGO's arms by less than 1/10,000th the diameter of a proton. Yet LIGO can detect them. Since 2015, LIGO and similar detectors in Europe have detected dozens of gravitational waves from colliding black holes and neutron stars, opening an entirely new window on cosmic violence. The diversity of astronomical instruments reflects the complexity of the universe itself. Different phenomena radiate energy at different wavelengths, and a complete understanding requires observing across the entire spectrum from radio waves to gamma rays, supplemented by gravitational wave observations, and perhaps someday neutrino astronomy and other exotic techniques. Each new type of observation has revealed unexpected phenomena and answered questions while raising new ones. The instruments themselves, from Galileo's handheld telescope to continent-spanning radio arrays and space-based observatories, represent humanity's determination to see beyond the limits of our senses. Beyond simply observing the universe, humanity has reached out into space directly, sending robotic emissaries to explore the planets and moons of our solar system. These spacecraft have transformed worlds that were once merely points of light in telescopes into real places with landscapes and weather, geology, and perhaps even the potential for life. The exploration of the solar system represents one of the great adventures of the 20th and 21st centuries, a technological achievement that has fundamentally changed our perspective on our cosmic neighborhood. The space age began with simple satellites orbiting Earth, but within a few years, spacecraft were being sent to the moon and planets. The Soviet Union achieved the first lunar flyby in 1959, and both Soviet and American programs sent increasingly sophisticated probes to photograph the moon's surface and eventually land on it. The Apollo program, which placed 12 humans on the lunar surface between 1969 and 1972, remains the only time our species has walked on another world. The moon rocks returned by Apollo missions revolutionized our understanding of lunar history, revealing that the moon formed from debris ejected when a Mars-sized object collided with the young Earth over 4 billion years ago. Mars has attracted more exploration missions than any other planet. Early flybys in the 1960s returned disappointing images of a cratered, apparently dead world, but later missions revealed a planet of surprising complexity. The Viking landers, which reached Mars in 1976, conducted the first experiments designed to detect microbial life in Martian soil. The results were ambiguous, neither definitively showing life nor entirely ruling it out, and the question of Martian life remains unresolved. More recent missions have discovered extensive evidence of liquid water in Mars's past. Ancient river valleys, lake beds, and mineral deposits that form only in water demonstrate that early Mars had a thicker atmosphere and a warmer climate capable of sustaining liquid water on its surface for extended periods. The Mars rovers, particularly Spirit and Opportunity, which arrived in 2004, and Curiosity, which landed in 2012, transformed our understanding of the red planet by serving as robotic field geologists. They drove across the Martian surface for years, far longer than their design lifetimes, examining rocks and soil with sophisticated instruments. They found minerals that form in neutral pH water, suggesting that ancient Mars had conditions potentially suitable for life. The Perseverance rover, which landed in 2021, is collecting samples of Martian rock that a future mission will return to Earth for detailed laboratory analysis. These samples may finally answer whether life ever arose on Mars. The outer solar system, realm of the giant planets, has been explored by a handful of spacecraft on one-way journeys taking years or decades. Pioneer 10 and 11, launched in the early 1970s, were the first spacecraft to visit Jupiter and Saturn, returning images of swirling atmospheric storms and discovering new details about the planet's complex systems of rings and moons. The Voyager missions, launched in 1977, took advantage of a rare planetary alignment that occurs only once every 176 years to visit Jupiter, Saturn, Uranus, and Neptune in a single grand tour. Voyager's images revealed these worlds as dynamic and complex, with active atmospheres, intricate ring systems, and moons that proved to be worlds in their own right. Jupiter's moon Io, revealed by Voyager to be the most volcanically active body in the solar system, erupts sulfur and sulfur dioxide from hundreds of volcanoes, coating its surface in yellows and oranges and creating a constantly renewed landscape. Europa's smooth ice surface, crisscrossed with cracks and ridges, suggested an ocean beneath, kept liquid by tidal heating from Jupiter's gravity. Saturn's moon Titan, larger than the planet Mercury, was revealed to have a thick atmosphere of nitrogen and methane. Later missions would show that Titan has lakes and rivers of liquid methane and ethane on its surface, the only other world besides Earth known to have stable liquid on its surface, though at temperatures hundreds of degrees below zero, where water is as hard as rock. The Cassini mission, which orbited Saturn from 2004 to 2017, studied the ringed planet and its moons in unprecedented detail. It discovered geysers erupting from the south pole of the tiny moon Enceladus, shooting water ice and organic molecules into space from a subsurface ocean. It watched storms rage in Saturn's atmosphere and observed the planet's rings in exquisite detail, revealing them to be composed of countless particles of ice ranging in size from dust grains to houses, shepherded into narrow bands by the gravitational influence of small moons. Cassini deployed a probe called Huygens that descended through Titan's atmosphere and landed on its surface, the most distant landing of any spacecraft. The images from Titan's surface showed rounded ice boulders in a landscape carved by flowing methane. Beyond the giant planets lie the cold outer reaches of the solar system, where dwarf planets like Pluto orbit in the realm called the Kuiper Belt. New Horizons, launched in 2006, flew past Pluto in 2015 after a 9-year journey. The images it returned transformed Pluto from a fuzzy blob in telescopes into a world of nitrogen ice plains, water ice mountains reaching 2 miles high, and a hazy blue atmosphere slowly escaping into space. Pluto's large moon Charon showed its own complex geology, and 4 smaller moons orbited the system in a gravitational dance shaped by ancient impacts. Some spacecraft have ventured even farther, leaving the planetary realm entirely. Voyager 1 and 2, after completing their planetary tours, continued outward and have now crossed into interstellar space, the region beyond the influence of the solar wind. They continue to send back data about conditions in this unexplored frontier, though they are so distant that radio signals take more than 20 hours to reach Earth. These spacecraft carry golden records, phonograph discs encoded with sounds and images of Earth, messages to any extraterrestrial intelligence that might someday encounter them, though the chances of such an encounter are vanishingly small given the vast emptiness of space. Closer to home, spacecraft have visited asteroids and comets, the leftover building blocks of the solar system. The Rosetta mission, which arrived at Comet 67P in 2014, orbited the comet for 2 years and deployed a lander to its surface, studying how the comet changed as it approached the Sun and its ices began to vaporize. Sample return missions have brought back material from asteroids, allowing scientists to study pristine samples of the material from which the solar system formed. These missions revealed that asteroids contain water and organic molecules, the raw materials necessary for life, supporting the hypothesis that impacts by comets and asteroids may have delivered these materials to the young Earth. Each mission to another world has revealed unexpected complexity. The solar system is not a collection of simple static objects, but a diverse family of worlds, each with its own character and history. Exploration has shown us ice volcanoes on Triton, hydrocarbon lakes on Titan, ancient riverbeds on Mars, and subsurface oceans on Europa and Enceladus. It has given us perspective on Earth as one planet among many, sharing some characteristics with its siblings but unique in its temperate climate, liquid water oceans, and abundant life. As we look toward the future of astronomy, we stand at a remarkable moment in human history. The tools at our disposal have never been more powerful. The questions we can address have never been more profound, and the pace of discovery continues to accelerate. The coming decades promise to bring answers to questions that have puzzled humanity for millennia, while inevitably raising new mysteries that we cannot yet imagine. The next generation of ground-based telescopes, now under construction, will dwarf even the largest instruments operating today. The European Extremely Large Telescope, the Giant Magellan Telescope, and the 30-metre telescope will all have collecting areas many times larger than current facilities. These enormous instruments will be capable of directly imaging planets around nearby stars, not merely detecting their presence, but actually seeing them as separate points of light distinct from their parent stars. They will study the atmospheres of these exoplanets through spectroscopy, searching for chemical signatures that might indicate biological activity. The presence of oxygen and methane together in an atmosphere, for instance, would be difficult to explain without life, since these gases react with each other and must be continuously replenished by biological processes on Earth. Space-based observatories will complement these ground-based giants. The Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, will survey vast areas of sky to study dark energy, dark matter, and exoplanets. Its wide field of view will allow it to observe millions of galaxies and thousands of exoplanets, providing statistical understanding of cosmic structure and planetary systems. Future concepts include even more ambitious missions, space telescopes with mirrors dozens of feet across that could image Earth-like planets in detail, perhaps even detecting seasonal changes in vegetation or the lights of cities if technological civilizations exist beyond our solar system. The search for life beyond Earth will intensify with these new capabilities. Astronomers will not only search for chemical biosignatures in exoplanet atmospheres, but also look for technosignatures, evidence of technology created by intelligent civilizations. Radio telescopes continue to listen for artificial signals from space, extending the search for extraterrestrial intelligence that has been ongoing since 1960. New approaches look for other signs of technology, such as unusual infrared emissions that might indicate waste heat from advanced energy systems, or patterns of dimming around stars that could be caused by artificial structures. While the discovery of intelligent life beyond Earth remains uncertain, the question is now being pursued with scientific rigour and increasingly sophisticated tools. Gravitational wave astronomy will expand dramatically in the coming years. Ground-based detectors like LIGO and Virgo will be joined by additional facilities, creating a global network that can pinpoint the location of gravitational wave sources with greater accuracy. A space-based gravitational wave observatory called LISA, planned for the 2030s, will detect gravitational waves at lower frequencies than ground-based detectors can observe. LISA will consist of 3 spacecraft flying in formation millions of miles apart, using laser beams to measure the tiny distance changes caused by passing gravitational waves. It will detect collisions of supermassive black holes at the centres of distant galaxies, events too powerful and too low in frequency for ground-based detectors to observe. Multi-messenger astronomy, the simultaneous observation of cosmic events using multiple types of signals, represents a powerful new approach. When 2 neutron stars collided in 2017, astronomers detected gravitational waves from the collision, followed seconds later by gamma rays, then hours and days later by optical light, X-rays and radio waves. This single event, observed across the electromagnetic spectrum and through gravitational waves, provided insights that no single type of observation could have revealed alone. As detectors become more sensitive and collaborative networks more coordinated, multi-messenger observations will become routine, revealing the physics of the most violent events in the universe. Artificial intelligence and machine learning are transforming how astronomers analyze data. Modern telescopes and surveys generate data faster than humans can examine it. Automated systems identify interesting objects, classify galaxies, detect transient events like supernovae, and search for patterns in vast data sets. Machine learning algorithms can recognize subtle patterns that human observers might miss, discovering rare types of objects or detecting faint signals buried in noise. These tools do not replace human astronomers, but augment their capabilities, allowing them to focus on interpretation and theory, while computers handle the initial sorting and classification of overwhelming amounts of data. Closer to home, the exploration of our solar system will continue with increasingly ambitious missions. Plans exist for orbiting missions to Europa and Enceladus, perhaps eventually landing on these icy moons and drilling through to the subsurface oceans to search directly for life. Mars exploration continues toward the eventual goal of human missions, though the challenges of keeping humans alive during the months-long journey and on the Martian surface remain formidable. Missions to Venus, long neglected after early Soviet and American probes, are being reconsidered. Despite surface temperatures hot enough to melt lead and atmospheric pressure equivalent to being half a mile underwater on Earth, Venus's upper atmosphere is relatively benign and could potentially harbour microbial life floating in the cloud layers. The question of whether humans will eventually become a spacefaring species, establishing permanent settlements beyond Earth, remains open. The International Space Station has demonstrated that humans can live and work in space for extended periods, though the long-term health effects of low gravity remain concerning. The Moon may serve as a testing ground for technologies and techniques needed for more distant exploration. Water ice exists in permanently shadowed craters near the lunar poles, potentially providing resources for future lunar bases. Mars, despite its harsh environment, has the resources necessary to support human settlement if the technological and biological challenges can be overcome. Astronomy has always been driven by fundamental human curiosity, the desire to understand our place in the cosmos. The questions we ask have grown more sophisticated as our knowledge has expanded, but the underlying wonder remains unchanged. We still look up at the night sky with the same sense of awe that our ancient ancestors felt. We still seek to understand how the universe began, how it will end, whether we are alone, and what our existence means in the context of cosmic history. The tools we use to address these questions have evolved from naked eyes to space telescopes and gravitational wave detectors, but the impulse to explore and understand is timeless. As we develop ever more powerful instruments and techniques, we continue the ancient human tradition of seeking knowledge about the universe, pushing always at the boundaries of the known. Standing at the edge of what we know and gazing into the vast unknown, we find ourselves in a privileged moment in cosmic history. The universe is old enough that stars have lived and died, forging heavy elements and scattering them into space to form new generations of stars and planets. It is young enough that stars still shine brilliantly throughout the cosmos, galaxies still spiral through space, and the universe remains filled with light and structure. We exist in what might be called the golden age of the universe, a time when complexity and beauty flourish on cosmic scales. Our journey through the history of astronomy has taken us from ancient observers marking the seasons by stellar risings to modern scientists detecting gravitational waves from colliding black holes billions of light years away. This progression represents more than just technological advancement. It reflects a fundamental shift in human consciousness, an expanding awareness of our place within an almost incomprehensibly vast cosmos. Each discovery has simultaneously humbled us and elevated us, showing that we are smaller and less central than we imagined, yet also revealing that human minds can comprehend even the most distant and exotic phenomena. The universe we have discovered through astronomy is far stranger and more wonderful than our ancestors could have conceived. It is a universe that began in an unimaginably hot, dense state and has been expanding for nearly 14 billion years. It is a universe where space and time are woven together into a flexible fabric that can be warped by gravity and set rippling by cosmic violence. It is a universe where most of the matter is invisible, where a mysterious dark energy pushes galaxies apart with ever-increasing speed, where black holes tear apart the fabric of space-time, and where stars are born from clouds of gas and die in spectacular explosions that seed space with the elements necessary for life. We have learned that our solar system is one among hundreds of billions in our galaxy alone, and that our galaxy is one among hundreds of billions in the observable universe. The sheer scale is difficult to grasp. Light from the most distant galaxies we can see has been travelling toward us for more than 13 billion years, since shortly after the Big Bang. We observe those galaxies not as they are now, but as they were in the ancient past, seeing light that began its journey when the universe was young. Looking deep into space is looking back in time, and our most powerful telescopes are time machines revealing cosmic history. Yet for all we have learned, profound mysteries remain. We do not know what dark matter is, though it outweighs ordinary matter by a factor of 5. We do not understand dark energy, though it makes up 70% of the universe. We do not know if the laws of physics we have discovered apply throughout the cosmos, or if there are realms where different rules govern. We do not know if our universe is unique or one among many in a vast multiverse. We do not know if life exists elsewhere, or if Earth's biosphere represents a singular occurrence in cosmic history. These unknowns are not failures of astronomy, but frontiers, invitations to future discovery. The search for life beyond Earth may be the most profound question humanity can address. Are we alone in the universe? Or is life common, perhaps even inevitable, given the right conditions? The discovery of thousands of exoplanets has shown that worlds are abundant, and many appear to orbit within their stars' habitable zones. The detection of organic molecules in interstellar clouds and on comets and asteroids suggests that the chemical ingredients for life are widespread. The discovery of subsurface oceans on Europa and Enceladus has revealed that habitable environments may exist in places we never expected. Yet we have not yet found definitive evidence of life beyond Earth. The coming decades may finally answer this ancient question, or they may deepen the mystery by showing that despite abundant opportunities, life appears to be rare or even unique to our world. As we look to the far future, the universe's evolution seems already determined by the accelerating expansion driven by dark energy. Galaxies beyond our local group are receding faster and faster, and eventually they will move beyond the cosmic horizon, their light so redshifted that it becomes undetectable. Trillions of years from now, if any astronomers exist in that distant era, they will look out from their galaxy and see only darkness, the universe having expanded so much that all other galaxies have disappeared from view. They will inhabit a lonely cosmos with no evidence that an age of galaxies ever existed, unless ancient records survive to tell them of a time when the night sky was filled with light. Even the stars themselves will not last forever. Star formation requires cold gas, and eventually the reservoirs of gas will be exhausted. The universe will produce its last generation of stars, and then no more will be born. The smallest, coolest stars, the red dwarfs, burn so slowly that they can shine for trillions of years, but even they will eventually exhaust their fuel. White dwarfs will cool and fade, neutron stars will slow their spin, and black holes will slowly evaporate through a quantum process called Hawking radiation, over timescales so vast they make the current age of the universe seem like an eye blink. The far future appears to be one of increasing cold darkness and entropy, a gradual running down of all cosmic processes. Yet this distant fate does not diminish the wonder and beauty of the present moment. We live in an age of stars and galaxies, of planets and possibly life, of structure and complexity. We live at a time when intelligent beings can arise and contemplate the cosmos, using light that has travelled across space to reconstruct the history and nature of the universe itself. This is no small thing. The universe, through us, has become aware of itself. Atoms forged in stellar cores have organised themselves into structures complex enough to ponder their own origins. Astronomy reminds us that we are connected to the cosmos in the most literal sense. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were created in the nuclear furnaces of stars that died before our solar system formed. We are made of star stuff, as Carl Sagan eloquently observed, temporary arrangements of atoms borrowed from the universe and destined to return to it. This connection gives meaning and context to our existence. We are not separate from nature, but part of it, recent arrivals in a universe ancient beyond imagining, temporary witnesses to cosmic grandeur. As we continue to explore the universe through ever more sophisticated instruments and techniques, we honour the human impulse to seek understanding that began when our distant ancestors first gazed up at the night sky and wondered. The tools have changed, from naked eyes to space telescopes, from counting on fingers to supercomputers, but the fundamental questions endure. Where did we come from? How does the universe work? Are we alone? What is our place in the cosmic order? Astronomy may never answer all our questions, but the pursuit of answers reveals the universe in all its complexity and beauty. The night sky remains an invitation to wonder, a reminder that beyond our daily concerns lies a universe of astonishing scale and mystery. When we look up at the stars, We look across distances so vast that light itself requires years or centuries or millennia to traverse them. We see not just space, but time, viewing stars and galaxies as they were long ago, perhaps even as they were before Earth existed. In this act of observation, we participate in a tradition stretching back to the beginning of human consciousness, the simple act of looking upward and asking what lies beyond. The answers we have found through astronomy are more magnificent than any ancient myth, more wonderful than any fiction. The real universe, revealed through patient observation and careful reasoning, surpasses imagination.